All right, you guys.
Sixth grade.
So, I think everybody, or at least most of you guys, submitted, again, that PhET simulation, that game on torques and basically balancing beams. Most of you, I think, submitted that. If you haven't, right, it's just like any other late assignment. It's not a big deal. As long as you get that submitted to me before we take this test.
When's the test?
It won't be for a while. This is a longer unit. We're like, I think, a third the way through it, right? There's a lot to cover and kind of review. So we got a while for this test. Is that a question or?
No.
Okay. So don't worry about it, but I want to remind you, I would get it in as soon as you can, cross off your list, right? Stay on track. Part of this homework was the game, right? Just a screenshot of you finish all the rounds, show me what you got. I don't care your score, right? If you miss stuff, hopefully you figured out why. And then the second part was the worksheet, right? This was a bunch of torque questions and equilibrium questions that we needed to do to start practicing. Okay, I know what a torque is. It's a force times a perpendicular distance. I know it causes rotation. How do I figure out how they balance each other out? That's what all of these were about, right? And these were, if you noticed, it's at 90 degrees. These are the simple cases where the forces, they point straight up or straight down. So all you do is take force times distance, right? So I wanted to start you off easy, figure out how to add torques, sum them together so they add up to 0, and figure out which one's missing. The homework that I'm going to assign for tonight is same thing, but now the torques or the forces, they're applied at angles. So we got to break it into the x and y components.
And do like sine or whatever.
Yep. And basically you'll see one of the forces in the x direction will run through the point of rotation. So you ignore it, right? Because it's not any distance away from the point of rotation. So you can ignore half of it. Then you have the other component of the actual force, say points up. Now you have torques, force times perpendicular distance.
So
but it takes an extra step to do the trigonometry, right? Sine and cosine. Then you do the torques, the summation, equilibrium, all the same. What's up, Josh?
So are we going to be expanding off this, like doing what we've been doing, just on more complex things, or are we going to be like doing other equations on top of this?
A little bit of both, right? We're going to keep building on torque. The assignment.
This is actually going to be the unit, or whether there's still like a whole other like.
There's more. There's two parts. The first part is learning about torque. It's this twisting force, what it is, how we find it, how we calculate equilibrium. The second part is, I had you review it a little bit, we got to go back to rotational motion, circular motion, right? Angular position, angular speed, and angular acceleration. Because now we have a rotation force. So we need to calculate, instead of F equals ma, we're going to do tau equals I omega. Instead of calculating linear speed, we're going to calculate angular speed. So in this unit, there's torque and circular motion. Torques cause circular motion. So there's more coming. A lot of it's going to be review, but we need to connect the dots. There's a lot of parallels you'll see that'll help, but we're kind of in the circular rotational world right now. Not linear. So both is the answer to your question. Right now we're still figuring torque out. We're nailing that down. Then we're going to take this, okay, we learned about torque. Now apply it to circular motion.
Okay.
Yep. It'll make sense. I'm going piece by piece. But right now this piece is just about torque. We'll start circular motion today. I'm going to talk about it a little bit. And yes. So the homework for tonight is half of, more torque problems, equilibrium. The other half is intro circular motion or rotational motion stuff. Today, I want to start by reviewing this worksheet, right? This was due today. I want you, if you got this done, I want you to turn it in. Before, I want to ask, is there any of these that tripped you up or you want to talk about?
9.
Number 9? 9 and 10?
And also, I don't know how quick this will take. It won't take very long. I don't understand, number 1 for some reason I did wrong. I don't know what.
Number 1?
This doesn't move.
Okay. Is there one more that I can go over?
7.
Number 7. Okay. I'm going to bring this over here on the board. Oh, I should project this. Oh, why did I put that down? Dang it. I'm not thinking.
You can just write on
I could. I would not. I'd be in some trouble. Okay. Oh, that stupid glare.
it.
It's from the projector itself.
You glare on
Yeah, do you see it?
the Shut off the projector.
Right, of course. I just saw the answer. Nothing wrong. I'm going to write off to the side. So let me pull up. Oh, it's over here. Okay, so number 1 we can start with. This should be nice and easy. Force. What is the force, right here, that you need to balance the beam over here? Right? This literally is a teeter-totter, a balance beam. Here's your pivot point. So this, when I do rotations, the point that I choose to figure, that's what I'm going to assume rotation happens. So I'm going to add up all the torques around that point. I always label as O. It's just convention. I see in all my classes, that's what I do. You could call it Z, whatever you want. But I always label hey, this point is the point of rotation that I'm going to calculate all of the twisting forces around that point. So first of all, we have 1 force and 2 forces, right? Those are the only 2 forces acting. So those are the only 2 things creating torque or twisting forces about this point of rotation. What you basically are going to do is you're going to sum all the torques. Again, I put tau 0 to indicate I'm finding torques about point O or 0, whatever you want to think about. I don't care. Right? I know if everything is balanced, they're going to add up to 0. This twist and this twist are going to cancel out so that no rotation happens. Right? This is my equilibrium equation. Same thing I did when I added all the forces in the y direction. If it's not moving, or rather not accelerating, all the forces in that direction add up to 0, because I know there's no acceleration. This is asking, how do you balance it? Well, if it's balanced, it's just sitting there, not rotating at all. So I know right away, everything has to add up to 0. First thing is okay, this force, right? The force is pulling down. What kind of rotation would it create about this point? Would it spin this way, counterclockwise, or would it spin clockwise? Counterclockwise. If I pull here, the beam is going to rotate like this about that point. That is counterclockwise. Is counterclockwise rotation positive or negative? Positive. You could either remember clockwise negative, counterclockwise positive, or you could remember your right hand rule. Right hand, thumb out. I take my fingers and curl in the direction that rotation happens. This is pointed outwards towards me. That's positive. So this 0 equals positive. What's the value of the torque? The twisting force from here. How do I quantify how strong that twist is? 8 newtons. Then what do I do? What's torque? What distance? To the pivot point, right? Specifically, I'm going to overemphasize so you get this in your head. It's the perpendicular distance from force to pivot point. Well, this is already 90 degrees, so that distance, that's 50 centimeters, right? Now, I really should be doing this in meters. So I'm going to take, what would that be? 0.5. Double checking my math. Force times distance, perpendicular distance, is the torque. And it's a positive, good. Over here, we know the force pulls down. It shows us that much. We don't know how strong it is. First question would be, if this force pulls down, does it create a positive or negative rotation? Which one? Yeah, this force pulls down, rotates like this, right? That's clockwise, which is negative. Right-hand rule could say it curls this way. That's pointed away from me or into the board, into the paper. That's a negative. So this whole value is going to be negative. The force, the magnitude, we don't know that. So that's what we're missing. I need to multiply by the perpendicular distance to the pivot point. Well, here's 100, here's 175. The distance between those two, 75 centimeters or 0.75 meters. Now, I have a complete equation showing that these two torques add up to equal 0, showing me that it's in equilibrium or it's balanced. It's not rotating, or rather not accelerating, to be precise. Well, I have one equation, one unknown. I just do some math. Right? Multiply these together, subtract it over here. The negative sides would cancel each other. I got to get rid of this, so I divide by 0.75 on both sides, and this answer would tell me what the magnitude of the force you would need so that the whole thing is balanced. What did you guys get? 5.3, 5.3. I got 5.3. Good. F equals 5.3 newtons. Does that make sense? We all feeling all right about that? Use our equilibrium equation where all the torques about some point have to add up to 0 if it's balanced. Find the individual torques and write them according to our equation for torque is the force times perpendicular distance to the pivot point. Then you just add them up. Algebra. Solve for the one variable you don't know. Bada bing, bada boom. Okay? So that's number 1. Oh. Number 7, right? That was another one that you guys wanted to look at. So if you flip over on the back, erase this. Number 7, you have the mass of the bird standing on this bar or this stick. Notice, it tells you the mass of the stick. That means you have to include it in your calculations. If it ever says a bar of negligible mass, that's when it's saying, hey, assume this bar is magically without a mass. If it gives you the mass or the weight of the bar, you have to include it because it's pulling somehow and it's wanting to twist itself about whatever point you pick. You attach the stick to the wall by a hinge, lets it rotate, and then you got a piece of rope on the other end. The rope you ignore the mass of. It just holds it up. I want the force of the rope. Tension. So if I draw my forces, I got this force of tension, the bird's force, mg points down, and I have the mass, the weight of the stick itself that's contributing to the torque. I can't ignore that. I want to know the tension. Well, here I'm like, well, I can't add up all the forces in the y direction. I know these two, and I don't know this one, but here's x and y forces. So I can't just add forces in the y direction, because I don't know what's going on up here. I have too many unknowns. Well, we can do the torques. If I don't know any forces at this point, this would be the rotation point that I would want to pick. Because if I pick this point, whatever is applied here doesn't affect the torque. So you're not going to have them in your equation. That's where you would want to be strategic. If I picked some of the torques about this point, well, the tension runs through it, so I automatically get rid of that in my equation. I'm never going to find it that way. So I want to pick here, this is going to be my O. Again, equilibrium. Some of the torques about point O, this is a balanced situation. They have to add up to 0. There's no rotation happening. Then I got to go one by one. So really, I would start at the rotation point and move to the right. Oh, here's a force. That force, mg, 1 kilogram times 9.8 newtons. Do you agree that's the force of the stick? The weight of the stick? So 0 equals 9.8 newtons. How far is it from that point of rotation? 0.6. Even look and say, hey, the stick itself is 1.2 meters. If it's a uniform stick, its weight acts right through its center of gravity, right in the middle of it. Right in the middle is halfway, 0.6 meters. Does that create a positive or a negative twist torque? Going to twist this way, that's negative. Or you see, oh, clockwise is negative. This is really important. This will mess you up. Go slow when you think through this. Whether you use the right-hand rule, that's what I always do. Do it every time. Don't fly through it, right? Be methodical. That torque has to be negative, I know that. Move over. Oh, I got another force. The mass of that bird, 0.75 times 9.8. I have no idea what that actually is. 7.35? Yeah. Okay. So that force is 7.35 newtons. All right? 7.35 newtons. What is the perpendicular distance from that force to the point of rotation? 0.9. The problem listed, hey, the bird's 0.9 meters from the edge. 0.9 meters. Again, is that a positive or negative torque? Negative. Again, it's rotating clockwise about this point. Okay, that's negative. Right-hand rule, it's twisting this way. My thumb is pointed into the paper. That's the negative direction. This guy is a negative torque. So you can see these two forces add together to create a really strong negative twist. Intuitively, you should think, okay, the rope is the only thing counteracting that. You'll see it in the math, right? T, we don't know that force. We got to leave it labeled as T for tension, whatever you want. How far, what's the perpendicular distance from that force to the point of rotation? Everybody see that? This force is acting 1.2 meters from that point of rotation that I'm doing. 1.2 meters. Is that a positive or negative torque? Imagine this force pulls up. It's going to pull the bar this way. That's counterclockwise, which is positive. Right-hand rule spins this way, points out at me. That's a positive torque. You have your equilibrium equation. Find this number, find this number. They add up to be a big negative number. Move it to the other side. Divide by 1.2 on both sides, and all you get is T, the tension force. I got 10.4 newtons.
I got 10.4 newtons, but I did it differently.
How did you do it differently?
You might want to come and just look at it rather than try to like verbalize it to you.
Yeah.
The only thing I did that could have been, like you mentioned, that it did like negatives, but I did math.
Yep, that's 1.4.
And then.
You did exactly what we did.
I did?
Yeah. Josh said he did it differently.
You wrote it differently, though.
All Josh did is he wrote this equation, but he put these numbers over here. So you basically...
You just wrote it differently than
Yeah.
I did. Oh, okay. Yeah, sorry.
You're good. Yo, you're good. Have confidence. You did it right.
Yeah.
You basically you wrote all the negative torques here and the positives on the other side. Well, that's the same thing we did.
Yeah, I just...
I always
It's
do...
kind of just like cutting out a step.
Yeah.
The negatives.
Just be careful that you're methodical. Like any negative goes on the left, any negative or positive goes on the right.
Yeah.
I always do it this way because this always works. I know they have to equal 0. One side has to be 0. On the right side, I just designate, is it a positive or negative, and my math works. If you know they add up to 0, you could put the negative torques on the left, positive torques on the right, and solve. It's exactly the same.
Okay.
I encourage you to do this. This is truly using the equilibrium equation, plugging in and solving. If not, if that works for you, Josh, go with it, but stick with it.
Right.
Good question, though. All right, 10.4. We good? We use equilibrium equation. All the twists have to balance out, cancel out. That's what equilibrium means. I got to identify all the twists individually
What?
with the one missing thing, and then solve for my one missing thing. Okay?
Okay, we got it.
That's true.
Everybody feel okay with that one?
We do 8. Or
Yeah. I want to give you time to work later, but I don't have a ton that I want to cover today. I just want to give you time to work.
I just
Okay?
want to see how you set it up.
Okay. 2 masses. 3 kg and 5 kg are on this balance beam or teeter-totter. It's a meter stick, so if we need distance, we got that. If the mass of the meter stick is negligible, right? This weight, right? We don't include that. It said the mass of this stick is negligible. We can eliminate that. It's asking you, guys, what distance from the left, x, we'll call it, should the pivot point be placed so that these are balanced? This is different. This isn't saying, hey, what force balances this situation? It's saying you got these forces. Where do you put this so that it is balanced? There's only one point when the 2 torques will balance each other out and remain stable or in equilibrium. If you shift it, it's going to tip one way or the other. But the process is exactly the same. The trick is, let's call this x2. Here's the trick. Here's what the process you should do. You're like, okay, I need to use my equilibrium equation. This point will be O, that's my point of rotation. I'm going to find a situation where this thing's balanced. That means all torques, all twisting forces have to cancel out. Okay, so if I go, okay, this is a force. This force, 3 times 9.8, 29.4, thank you. We agree with that? This was a mass, that's not a force. I need to find the force of gravity pulling. mg gives me this many newtons. Over here I got a force, 5 times 9.8, 49. Oh, duh, I knew that. These are the 2 forces. So first one, 29.4. How far away is this force from the point of rotation? X1, good.
Yeah.
That is the distance. We don't know it. We're going to represent it by X1. Is that creating a positive or negative torque?
Positive.
Twisting this way, 1. Okay, that's counterclockwise, positive. Right-hand rule points out at me, positive. Second force is over here. 49 newtons times x2. That's the perpendicular distance from that force to rotation. x2. Is that a positive or negative torque? Again, I do right-hand rule, so I always go, okay, it's curling this way. That's negative. This is great. This is what you should start with. This is a good thought process. But you run into a problem. Flip. I got 2 variables in one equation. That's not solvable. We need another equation that helps us figure out x1, x2. Does anybody know an equation that lets us relate x1 and 2 that we could then add in here to solve?
Alright, I don't know if this is what, so I did it completely different from you, but, for, I guess on the left side of that, we put x minus 1, and then the right side we put x, and that's how we solved it.
What is x in your situation? What does x mean?
X is the length on the right side of the pivot point.
Why are you subtracting 1?
So because the length of it is 1 meter.
Okay, so they assumed this whole thing is 1.
It says a meter stick.
Okay, you're right.
Okay.
So that's what.
You didn't have to. You could have left it general. You could have listed any number. But that's a great point, and I'm going to go with that. Because you're right. If you carefully read, it does say meter stick.
But I just realized
That's 1
now.
meter.
We didn't realize that till just now, but it actually said meter stick.
If it didn't tell you the length, it really doesn't matter. You could have said it's 100. Because you're going to tell me, if it's 100, I'm going to put it here. If it's 1, I'm going to put it here. That's all it's asking. In this case, a meter. 1 meter equals x1 plus x2. Do you agree with that?
Mm-hmm.
The total length is this plus this.
Yeah.
That's an easy equation. Now we have 2 equations and only 2 unknowns. Now we can solve this. What you do is rearrange this and say, I don't know what the... I guess it doesn't matter. But you would say x1 equals 1 minus x2. And I think that's exactly what you did, or the opposite. It don't matter.
Yeah.
Right? I'm going to rearrange this equation. And then now I have an equation for x1. If I plug it in here, instead of writing x1, I'm going to write 1 minus x2 for right here. Now, I only have 1 variable. I can solve this whole thing for x2. Then I could say, okay, I know what x2 means. Plug it back in here, solve for 1 unknown, x1, and you're good. So the trick of this is you do the correct process, which I hope you all did. You run into a wall. Like, crap, I need something else to help me figure this out. Then you think, wait, it's a meter long. Both of them added together equal 1. If I switch this equation, I could plug one part of it in. So what you would do, this would instead be 1 minus x2. Then you just do your math. You'd have to distribute 29.4 minus 29.4 x2 minus 49 x2. Right? Move this to the other side, combine your x2's, and then divide by whatever that coefficient is. I got x2 to be... Oh, I didn't even solve for it. I was strategic because the question asked me, how far from the left should this point be? Well, that's x1. I solved directly for x1. if you solve for x2, it's just plug it in here, do a quick subtraction. x1 was 0.625. x2 would have been,
0.375.
thank you, I was trying to do that.
We're gonna think our way's easier.
What do you mean your way?
Come here. You guys, I don't know, like, once again. Like, we got the same answer, but we did like a fourth of what we did.
No, this is what you did the same thing. Equilibrium.
We didn't have
Equilibrium.
the 29.4 and the 49. We didn't solve for that. We just ignored all.
So you kept it as mg and said, I got g's on both sides, slashing. That's good.
Okay.
You're
yeah,
technically you are.
I don't know what we technically did, but we got the same answer and like 10 times easier.
The other trick that you'll learn, I'll help you with this. This is an ideal scenario where it's a flat beam, two forces, and somewhere we're in the middle, right? So you can set up like this ratio if you wanted to, right? This force, it's 3 times g. The ratio of left to right equals the opposite of the distances. The greater the force on the left, the shorter the distance should be. Right? So this would actually be equal to the opposite of the distances. Right? x2, x1. This ratio should be true. Well, then you could say 1 equals x1 plus x2, right? Say x2 equals 1 minus x1. This ratio should equal 3/5. So this, if I cross multiply, I got 5 minus 5x1 equals 3x1. This gives me 8x1, right? What's 5 divided by 8?
0.375. 5 divided by 8?
0.625
Oh yeah, sorry. Other number.
equals x1. Boom. This is an ideal situation. Straight beam, only two forces, and you want to find the balance point. The ratio of the forces on each end is inversely proportional to their distances. Right? Little force needs big distance to create torque to balance little distance, big force. So you could have done just a simple proportion and skipped the true physics because you know the symmetry of a problem. Don't worry about this. This is something that I remember from like my statics class. It's like a shortcut for ideal cases.
I'm saying because we didn't do like.
And yours is very similar to this.
Okay, because I don't understand what you were doing on the first part, but all I know we got the same answer, and my logic makes sense to me.
Okay. That's a good one. Now you want 9?
This too.
Yeah, I like this one.
I don't want this one.
Again, I've done this so much and
Well, I hope so.
I've gotten used to the challenge of it, but okay, 400 newtons. That's this guy.
Wait, The beam's 400 newtons.
Oh, thank you. Good catch, Josh. So, 400 newtons. This, it says uniform diving board. That means all the mass and weight, it's distributed evenly, so all the weight of that beam, the board, acts right down the middle of it. So that's why I put this right in the middle. The mass of the diver, I'm going to put it in force, 75 times 9.8, 735. Right? Those are two forces from the board, force from the diver. Okay? It's wanting me to identify F1 and F2. I got two unknown support forces. If it was just one of them, right, I could do sum of the force in the y direction. This has to equal this. I can't do that, though. I would have two unknowns. I need another equation. Well, let's just skip all that. If I look at my torque equilibrium, the first thing, this is what I was talking to you, Josh, when you sum all of the torques, the twist forces, it has to be about 1 point. Your pivot point, you get to choose. If this is truly balanced, any point in that beam, all of the twisting forces are balanced on either side. We know this is an equilibrium. It's not moving, it's not rotating. So you get to choose where you want your pivot point to be. There are good choices for the pivot point, and there are bad choices for the pivot point.
I think we probably chose what you consider bad.
An example of a bad pivot point choice would be, I want to say the pivot point's right at the very end. On the D.
No, we chose the back. We chose the far back on F1. No, I thought you
Here?
Yeah.
That's good. That's fine. That should work.
Okay.
Hold on. The reason that this is a bad choice, first of all, one of my known forces goes right through that. Well, that would create zero torque, so I can't use this to help me solve the problem. This would create a torque, this creates a torque, and this creates a torque. Well, immediately you should be like, oh, well, frick. These are two unknowns. I would have one equation and two unknowns. I haven't made any progress. So this is a bad choice. A good choice is there a point I could pick that would eliminate one of the unknown forces? Yeah, I could pick either of these. If I choose this, what did I do? I chose the very far left. This I called my O, my pivot point, my rotation. The reason I did that is because this force acts straight through the pivot point. What's the perpendicular distance of that force about that point? How far is this point away from that pivot point? 0. This unknown force, this support force, if it acts straight through the pivot point, there's no torque. I don't need to consider this in my equilibrium. Well, now, I only have one missing piece of information. That I can solve. So I can be like, oh, good, I picked a good point. Sum of the torques about that point needs to equal 0. It's in equilibrium. Everything needs to be balanced. Okay, so I'll move to the right. Oh, here's a force. F2. This is another strategy. Did I truly know if both of these are pointed upwards? Am I 100% sure about that? No. At this point, it doesn't matter. I would get in the habit, always guess that they would point up. Right? Just always have that be your default. When you do the algebra, if my answer comes out to be negative, well, what happens if I have a negative force pointed up? Is that possible? No. I guess the opposite of what's true. So if I get a negative answer, I know, well, crap. In reality, it's not going up, it's going down. Because the answer was opposite of what I expected. So it doesn't matter what you choose. Make a guess. And then at the very end, if your answer is negative, that means you chose the wrong direction. So you just flip it. So here, F2, I'm going to assume it pushes up. That means it rotates this way. That's counterclockwise. Right-hand rule would be a positive. The distance is 0.5 meters. We agree with that? Keep moving to right. Here's my next force. 400, newtons. How far away is that from the left edge? Well, you know the weight of that beam acts straight through the middle of the beam. The beam's 2 meters start to finish. Halfway would be 1 meter away. Does that make a positive or negative torque? Right? It wants to twist clockwise or negative. So this torque is negative. Keep moving. I got one more. 735. How far away is that force from the pivot point? 2 meters. It's the length of the beam. To create a positive or negative torque? Also negative. Good. I have no other forces, no other torque, so I've accounted for all of them in my equilibrium equation. This is a number, this is a number. My one unknown, I can solve. Multiply, multiply. This creates a big negative that I would move over here. And I would divide it by 0.5. F2. I got 3740 newtons. Anybody else get that? Yeah? Okay, good. If you didn't, again, jot this down. Again, you got the answers. My logic in that is, I don't want you to just do it and like, maybe I got it, I don't know. I want you to do it, and if you got it wrong, on the spot, frick, I did something wrong. What did I miss? Go critique yourself. If you did it right, you have immediate confirmation. Okay, I did the process correctly. Now, the trick is...
This is where it confused me when you did the scientific.
Oh, so here, it asks both forces. I want F1 and F2. Well, I just found F2. Now, F1, you could find by, okay, let's sum the forces about this point. I could do the torques on both sides. Something a little simpler, less math is, now, all I have is X or Y forces. It's all just up or down. So I can use my equilibrium equations from last units, right? Sum the forces in the Y direction. This thing's not moving up or down, so anything pushing up and pushing down should cancel out. I got F1 pushing up. Again, I'm guessing. I'm assuming it points up, that it's a positive Y direction. F2 was 3740. I need to subtract 400 newtons and subtract 735 newtons. Right? Add all these guys up. Your answer, F1, is negative 2605. Your answer is negative, right? This is 3,000 minus something.
But that means the 3,000 should be negative then.
No. You assumed this is positive, so I put it in the positive direction.
Yeah.
You know this force points up. I guessed it was up here and it came out positive. That's like confirms that I guessed correctly. So that's going up. The weight of the beam is down, negative. Weight of the diver is down, negative.
That doesn't make any sense.
You do your math, right?
Okay, but you're taking 3,740 minus 400.
Minus 400 minus
How do you get a
735.
negative
Hold
number?
on. Minus 2,605, but I have to move it to the other side.
Why?
To equal.
It's algebra. 0 equals this plus a positive. I need to subtract this number from both sides. 0 minus 2605 is negative 2605. It's basic algebra. Don't miss that. Do you agree with me? This minus this minus this was a positive number, right? 3,000
Okay.
minus basically 1,100 gives me 2,600. How do I get F1 by itself? Subtract 2605, but I have to do it for both sides. What's 0 minus 2605? Negative. This is where you're like, well, crap. I can't have a negative force going up. What this means is my answer is exactly opposite of what I guessed it was. In reality, F1 is going like that. F1 is pulling on the beam.
Oh, okay.
It's not, this support isn't shoving the beam up. If it did, the whole thing would flip, right? These forces would pull it. These forces would push it. You would spin like this. You'd fall. That means this force is the only thing stopping it from flipping. And if you really pause and think about it, if I put a ton of weight on the end, isn't the board wanting to snap and fall this way?
Yeah.
Well, if the board goes like this, wouldn't it separate right here?
Mm-hmm.
Well, the only way that that beam can stop that is to try and hold it back. Keep it from pulling up. That's why that force is down. Does that make sense?
Yeah.
This is new. Either way, since you don't know either of them, just guess. When you guess, you have to keep your math organized. If you guessed it was pointed up, it's a positive y force. At the very end, your answer, if it's positive, it confirms that you guessed correctly. It all worked out. If you guess and it gets negative, that tells you your guess was in the wrong direction. The number is going to be right if you did your math right. But I chose the wrong direction. So in your head, you need to realize a negative force going up is actually just that force, but flipped. Does that make sense? That's a tricky one because there's two steps, and it's a little different having two unknowns. I want to remind you, use your torque equilibrium. Choose a point that eliminates one of your variables. Make it easy on yourself. You can solve. Then you could redo it again at a different point to solve for the other missing variable. Or you could use another simple equilibrium and find it. When you guess, keep your sign conventions correct, and your final answer will tell you, oh, you guessed correct, or no, you guessed backwards. Feel good about that one? That's a good problem. That's a good, tough one.
You can say that again.
Key points. If you have two unknowns, choose your pivot point at one of the unknowns to eliminate it. That's the key. That's a good strategy you need to be able to do. The other one is make sure you understand all your equilibrium equations because you can use those. Any questions about that one? Okay, real quick, I want to get through number 10 so that we can talk about rotational motion today. And I want to give you time to work. Okay? Okay, I'm going to have you guys help me. Tell me what I should be doing when I look at this problem. First, let's label the graph.
Yeah, put your forces. 650 on the block.
Okay, so you can say I'm 650 student. This is my student.
Yeah.
It's pointing down. Perfect. 650.
250 going down right in the middle of the sheet.
Good. It said my beam has a weight of 250. It's uniform, so it occurs right smack dab in the middle. Any other forces on the beam?
On the supports going up. The other.
Good. Right? I would recommend always guess positive, right? Just it's a default. It'll help you go through it faster. We'll call this F2. We'll call this F1. Now the distances are labeled. 5 meters is the whole beam. The student's 1.5 from the left. Those are all labeled. Everything in my problem is accounted for in my drawing to help me understand. This is much easier to understand than making a mental picture. What is the force of this support? Let's do some strategy. I need to use my torque equilibrium equation. What should I choose as the pivot point to let me, in one step, solve this? Where should my pivot point be? Here?
Yeah.
Why?
Because it's going to get rid of that here.
If I choose my pivot point here, this force acts straight through the pivot point. If it goes straight through the pivot point, the distance is 0. That means this couldn't create a torque about that point. So this is an excellent choice because this is now excluded from my equilibrium equation. You could include it, but it'd be F1 times 0. It eliminated itself. Now, I just have one unknown. One unknown, one equation you can do. Good. Again, some of the torques about my pivot point, O, equals 0. 0 is equal to, okay, here's my first force, 650 times 1.5. Positive or negative?
Negative.
Negative. Next force is 250 times 2.5. Do you see that? If it's acting straight in the middle of the beam, well, halfway through the beam is 2.5. It'd still be negative. It's pulling down. That's clockwise rotation. Or my right-hand rule pointing in, that's negative. One more force is F2 times 5. Positive or negative torque? Positive. It's going counterclockwise or positive. Bam. That's it. Solve. Plug and chug. Right? Do your math. Move it to the other side. Divide by 5. Solve for F2. At this point, it's pure algebra. What did you guys get?
You get 2,900, divide that by 5. Is 500.
I got 320.
Yeah, I got 320 as well.
Oh, then I was doing the other.
Yeah.
I was looking at the other board. So 60.
Pay attention. It's really important. When you do this math, you get a positive 320 newtons. That doesn't mean it's absolutely going up. What it means is we guessed it going up. If it's positive, we guessed correctly. Then you can confirm, okay, this truly is pushing up on the beam. We could have done this whole thing, but assumed, oh, I think it pulls down. A-okay, no change, except your answer would have been negative to show you, oh, you guessed wrong, just flip it. That's what's actually happening in the real world. Okay, perfect. I would recommend this step. You could sum the torques at any point. Couldn't care less what that is. It'll still work. Let's see, that's A. For B, I would sum the forces in the y direction. So then it's just add the 3 and find the missing one. Well, F1, I'm going to guess is up. I'm going to guess it's a positive. Minus 650, minus 250, plus 320, because I confirmed that force indeed does push up. If you mix that or jumble it up, you're going to botch the other part of it. Okay? Now, negative, negative, positive, right? Add them all up. Flip them to the other side. F1, 580. Again, the math told us it was positive. Right? This is a huge negative. Cut off a portion of it. I got to move it to the other side. F1 equals a positive 580. You can't assume that means it's pointing up. What that confirms is you guessed the direction correctly in your math. Then you can say, I know for sure, I guessed correctly and it's positive, so I can confirm it is pointing up. It's truly a positive y force. Forces are vectors. You have to tell me the correct number and the correct direction. Right? So there you got both support forces. Answers A and B. Does that help?
Yep.
Again, they're not terrible. If you're methodical, you do the sum of the torques equal to 0 because I know it's balanced. Where are all the torques at? Confirm that they're positive, negative. Do your algebra. Confirm if your answer is agreeing with your assumption or not to understand what's physically happening. That's all it is. Being strategic because in this situation, it's not add all the ups and add all the downs. You don't get a choice in that. This, sum of the force in the wire extraction, there's no choice. When you do torques, you get to choose. Any point's going to work, but it's up to you. So be strategic. The key is choose a point of rotation for your equilibrium equation that eliminates one of the unknowns. That's a key basic skill. They're going to do this. You're going to be given two unknowns. You've got to figure out, crap, I need to put my point of rotation at an unknown in order to solve this problem. Otherwise, you're going to do a lot of work and you're going to get two unknowns. All for nothing. That's a big takeaway, especially from this worksheet. Tuck that away because AP questions, if I was writing an AP test, I would guarantee to have something like this. To force you to demonstrate to me that you understand how to use torque equilibrium and how to use it strategically. All right? Okay. Oh, that took way longer than I thought.
No, we got time. Just give it to us now.
Flip. Yikes. Okay. First of all, though, was that useful?
Yes,
Extremely.
very.
This
Okay.
is why we don't. This is why we have 8, 9, and 10.
Okay. I appreciate that because I never want to waste your time. This class time is precious. I want to use it to your benefit.
This helps so much.
Good.
Yeah.
This makes me feel good. I'm A-okay that we spent, an hour straight on this?
Dang years old.
That's good. I'm happy with that, even though it wasn't what I planned. That's A-okay. Next thing I want to talk about, how do I want to talk about it, though? Okay. So I need to talk about this. This is where I need you to get notes out. Please, even if you don't think you take notes, please do it now. Because the best way is for us to get these equations down. So that we know how to use them. Okay? What is this?
I really hope not. I already forgot about my use.
It's not unit circle. At least it's a basic part of it. Okay, guys, this is really important. This, like what I was talking about, this unit is torque and rotational motion. I needed to introduce torque because that's the twisting force. The twisting force is what drives or causes rotational motion. You can't have rotation, or rather, you can't have a rotational acceleration. You can't change your rotation unless you have a torque. That's why I spent all this time telling you what a torque is, understanding the equations, how to calculate a torque, and now how to use equilibrium equations to demonstrate that all the torques on an object balance out if the object is truly in equilibrium or not in rotational motion. Now we need to connect it to the rotational motion that occurs. This is the same way that we talked about, we did it backwards. We talked about linear motion. We learned about position, speed, and acceleration. Then we learned about force and learned, okay, F equals ma. Force causes motion. I'm doing it backwards where we learned about torque, the driving force of rotation. Now we need to talk about angular position, angular speed, and angular acceleration. These are two parallel worlds. In these parallel worlds, one world is linear, straight motion, left, right. You could go diagonal. It's just translational. The other world is spinning. I speed up, I slow down, I keep spinning, I stop. These two parallel worlds, force and torque, are synonymous. Force causes linear motion. Torque causes spinning motion. A linear position, what variable do we use to demonstrate linear position? Translational is linear. What variable did we use to describe an object's position? X. The variable x told you where it's located in linear space. In rotational world, you guys have seen the theta. It's a little blurry. This is an O with a line slash through it. Theta, that measures the angular position, right? I'm 90 degrees from 0. I'm 180 degrees rotated away from 0. They're synonymous, but they're different worlds. Do you see the parallels, though? I'm not telling you how far away in a line I am from a start line. I'm telling you how far away in the rotation I am from this 0 point. The next step, we talked about position. Then we talked about speed. How does your position change over time? If it's changing quickly, you're moving fast. 10 miles every hour. In rotational world, that's angular speed. How fast are you spinning? How many degrees are you covering per second? That's this omega. Theta, omega. It's like this rounded off W. That's omega. That is the variable we use to talk about angular speed. How fast you're spinning. What, Josh?
So I thought omega was like the upside down horseshoe.
That's a capital omega.
Oh, okay.
Yes. That's also omega.
Okay.
They're all Greek letters. One's capital, one's lowercase.
Okay, I did not know that.
Good question.
All right.
Good question. So just so you know, theta and omega, angular position, angular speed. What did we learn after we learned about position and speed? Acceleration. We learned about position, then how your position changes with time, that's speed, and then how your speed changes with time. That was acceleration. Are you speeding up, or are you slowing down, or are you changing direction? All of those were acceleration, but in this linear world. Flip to circular world, you still have acceleration, but it's angular acceleration. Is your rotation spinning up, like speeding up, or are you spinning fast and slowing down? Do you see they're literally two sides of the coin? One is in this linear left, right, up, down world. The other is in a spinning world. I need you to see that they're parallels because if you look, the equations are the same. We just use different variables. The last variable is an alpha. Angular acceleration is an alpha. When you type it, it's hard to... It's like this. It's like an A with two tails. I can't take the time to draw that the way it should be, so I draw like... It's kind of like the fish, right? Have you seen like the fish? Like that? I draw that shape. That's how I draw alphas, because it's quick and easy and still looks like an alpha, so people understand what I'm writing.
That's what that is on it.
That's what, it's hard to see.
Okay.
It's not an A,
Yeah, thank you.
it's an alpha. Yes, thank you, Brody. You can see them a little bit. Here's your theta. That's the angular position. How many degrees are you from the start point. Omega is how fast you're spinning. How many degrees are you covering in a second? Alpha is, are you speeding up or are you slowing down?
It is fast.
Right? I really need you to see these are literal mirrors of each other. Position, linear position. Rotational speed, linear speed. This is angular acceleration, linear acceleration. Time's the same in both. Time doesn't change either way. All these equations are the same. It's crucial that you understand that because it helps you. You've already learned about this stuff. We've seen this before. We've learned position, speed, acceleration. Well, now we're going to do the exact same thing, but it's not in a straight line. It's spinning. That's it. So you need to know these variables: angular position, angular speed, angular acceleration. I would jot these down. Also, I think these are also in your equation sheet. This guy is in your equation sheet. There's another one, another kinematics equation that's not on here, that is on your sheet. Your equation for torque is on your sheet. Another thing that I want to point out that you'll need for your assignment just to help. There's a lot more information that we could talk about, right? Here's another one. You know, counterclockwise rotation is positive. You're increasing in the positive direction. If you spin clockwise, you're spinning in the negative direction. You guys should know, in one complete revolution, you have 360 degrees. That's important to understand. This is another equation that you need to know. The arc length, the length that you would travel if you're going in a circle, like how far this distance is, you can calculate if you know the radius of the circular motion and how many degrees you move. Now be careful. This isn't 10 degrees by 1 meter. The standard for measuring angles is radians. Right? Now let's think about this. You guys remember your unit circle? Yeah. I'm going to bring it up for a second. What was one complete circle equal to? How many? 2 pi. That's a crucial fact that I need you to jam in your brains and never forget. One revolution is 2 pi radians. Just to clarify, pi is a number. It's not 2 pi's. It's 2 times 3.14159269358, whatever it is.
Okay.
6.28, blah, 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 radians. There are 6.2 radians in one complete revolution. Degrees and radians are 2 ways to measure angles. We really want to focus on radians. Our equations use radians. So how would you convert degrees to radians? Well, that's easy. 180 degrees is half of a circle, right? Half of a rotation. Half of a full rotation is half of this. Well, 2 pi over 2 is pi radians. If you want to, 360. A complete rotation in degrees is 360 degrees. That's 2 pi radians. If you ever need to convert, right, you rotate 75 degrees. How many radians is that? Well, 75 degrees, there's 180 degrees per pi radian. Just do a unit conversion. All right, this is really important. We always want to be in radians. So get in the habit of thinking in radians, which is a measure of an angle. Okay? I think I talked about this. You'll need to know this equation. The distance that you travel along a circle path, literally this length, that's S, arc length. You can calculate that by finding the radius, not diameter, the radius of your circular motion times how many degrees you sweep or move, right? I wouldn't take 1 meter times 90 degrees. That would give me 90 meter degrees. That's not a unit of length. Radians is unique. Radians is technically unitless. I want to prove it to you because if this is the equation for radian, theta is my radian. So if I get theta by itself, I need to take S divided by R. S is this length, which is in meters. Radius is this length, which is in meters. What's a meter divided by a meter? Nothing. That's a mathematical proof that a radian is unitless. That's important to remember if you're trying to figure out units. Essentially, this means that 1 radian is the ratio of arc length to radius. Arc length over radius. That's where it comes from, that's what it means. But I really need you to know that it's unitless. Omega. What is omega? Angular velocity or angular speed. How fast you're spinning. Well, in linear world, speed was distance over time. We don't measure distance, we measure angle. So omega, omega is angular distance over time. Same exact thing, but we're in a different world. Omega is the change in position, or change in theta, divided by the change in time. Notice, this is radians over seconds. You could write radians per second. That works. But a radian is unitless. So technically, your units for angular speed is 1 over seconds. Really goofy. If it helps you, write radians per second. Because then it reminds you, okay, it's this many degrees per second. But just know, mathematically, a radian has no units. That's a weird quirk. Don't do that, that's calc. Here, down here, the acceleration, angular acceleration, is the change in angular speed over time. So you would do like omega final minus omega initial over time. Same thing you would do in linear motion. Acceleration is how your speed changes over time. Angular acceleration is how your speed changes over time. Your units, radians per second. Radian per second squared. Or, technically, it's 1 over second squared. Either one, I personally recommend doing this because it helps remind you I'm talking about a radian, which is an angle, over time. Per time. Another thing you're going to need to know where's my tangential? So there's again another comparison. We talked about how the quantities, they're the same, they're parallels of each other. The equations are parallels of each other. This one, you'll need to know this. Tangential speed. If I got something spinning, the speed of rotation is omega. But there's a linear speed of my spinning object at the very tip, right? It's moving at, say, 20 miles an hour at the end of the string, say. It has a linear speed, but that linear speed is constantly being changed. Here is your tangential speed. Angular speed is how fast it's rotating. You can convert between the two by this equation. If you take the angular speed times the radius of rotation, that tells you the linear speed at that point. I want to remind you guys, the word tangential means it's a tangent. Tangential speed will always form a line with the circle, the motion, that touches at exactly one point. It's important to remember that, because some of you guys forget, they think tangential speed is going this way, maybe it's pointing down. Tangential speed is always touching the circular motion and pointing out in the direction of motion. That equation is just radius times angular speed. You'll need that one. And I think that's it. Oh, one more that's helpful. Here's another one. Tangential acceleration. Tangential speed was radius times linear or angular speed. Well, it's no surprise that tangential acceleration is radius times angular acceleration. Basically, to convert from the angular unit into the linear unit, multiply by the radius. It's not true for every single value, but for the position, speed, and acceleration, it is true. Acceleration tangential, the acceleration in this direction, is r times alpha. Another one that you don't need right now, but you will. Do you remember the centripetal acceleration? What did that do? What did the centripetal acceleration do? It caused what type of motion? Circular. You're on a merry-go-round. You should be going straight, but something constantly pulls you towards the middle into a circle. That is the centripetal acceleration or centripetal force. It's always pointed this way. So the acceleration in this direction, which is linear, is equal to the radius times the speed squared. That's a little different. You won't need it, but put that down. We'll use it in the future. Okay, same thing. I got 2 worksheets. We didn't have a lot of time, so please do your best to complete these. The first one is the torque, just like the sheet you just did that we went over, but now the forces are at angles, right? They're not straight up and down. You got to convert them into x and y and think, wait, this one doesn't cause a torque, but this one does. So that's what I want to include in equilibrium. The second equation, or second worksheet, is intro problems to this stuff. Circular motion, right? Angular position, speed, and acceleration. Do your best, but we'll probably do the same thing we did today. I need you to try these and get as much done as you can, and then come next class with questions. I'll be able to help you. We can do the same thing. We can work through them. So don't stress out. Also, these worksheets, right? The torque at 90 degrees, the assignment's due today. Put it right here on your way out. Again, if you completed it, I'm going to give you points. Did I give you both of these? Okay, you got both. Yes, you can go. Again, guys, I'm sorry it was to the last minute. I appreciate that you guys let me know that this was helpful. That's really encouraging. That's my job, is to help you guys.
They were talking about any interior.
Way wrong,
I just told them whatever they want.
Did
Whatever they want. Probably what? If they have my Marion, I tackled a receiver from Marion, so
Again, your worksheet due today. Just stack it up on this cart. If it's not done, that's fine. Wrap it up and get it to me next class. Just please don't forget about it.